Good morning, this is Jaswinder Kaur and I'm here to start the new course on the linear transformation and is the lesson 1, the introduction part. Right, okay. The first one is the definition for the linear transformation. Suppose UF and VF are the two vector spaces over the same field F. Then a linear transformation T is a function from U into V. It is a function from U into V. What is into function? A function where the range is the proper subset of the codomain. Right? If suppose I'm having the elements A, B, C in this U domain. And here if I'm having the elements 1, 2, 3, 4. Then if suppose TA is equal to 1 and T of B gives the value 2. T of C gives the value 3. What is the range then? It is 1, 2, 3, the set 1, 2, 3 and this set is a subset of the set 1, 2, 3, 4, the 4 elements. This is your codomain. And this is the range. Right? So the function where the range is a subset of the codomain is your into function. Very fine. So here the linear transformation T is the into function from the vector space U to F, such that T of A alpha plus B beta, this will be equal to A into T alpha plus B into T beta for all alpha beta belonging to U and the scalars A, B belongs to F. Is it okay? Fine? Yes? Let me mark this equation as 1. Then this equation 1 is called the linearity property. It is the linearity property. Yes? Okay. Please note that this equation 1 is equivalent to the condition if I write T A alpha plus beta. I have not multiplied this beta with small b. I have taken only the scalar A, which is multiplied with alpha. Alpha beta is belonging to U. Right? So this is equal to A T alpha plus T beta. Right? For all alpha beta belonging to U and the scalar A belongs to F, the field F. All the scalars A in F. Second, linear transformation is also called vector space homomorphism. Please remember this. Right? Okay. Now let's move on to the linear operator. What is a linear operator? Let VF be a vector space. A linear operator on V is a function from V into V, the vector space into itself, such that T A alpha plus B beta is equal to A into T alpha plus B into T beta for all alpha beta belonging to V. It is from V into V, right? And for all A, B belonging to F. V is a vector space over the field F. So the scalars always belongs to the field F. For the linear operator, the function is from V into itself. For the transformation, the function is from U into V. U and V are the vector spaces, right? So what do you say about the linear operator? So therefore T is a linear operator on V if T is a linear transformation from V into V itself. So the linear operator T is a linear transformation from V into V itself. Alright, let's move on to one example. Let Vf be a vector space of all m by n matrices over F. P be a fixed matrix m by m and Q be n by n matrix. The correspondence T from V into V defined by T of A equal to PAQ for all A belonging to V is a linear operator on V. We need to show that this T is a linear operator on V, which means T is a linear transformation from V into V. Yes, we need to show this. So for that, if suppose this A, let's take this A to be m by n matrix, because it is given to us that Vf is a vector space of all m by n matrices. That is why, because A is belonging to V, so we have taken A to be the m by n matrix. Okay, then what matrix is PAQ? If P is multiplied with A and then further multiplied with Q, then this is also your m by n matrix over the field F. Please take care of this. Therefore, T is a function from V into V. Now let the two matrices, let's take two matrices from V and the scalars from the field F. To show that T is a linear transformation, we need to show the result, that T A into A plus B into B. This should be equal to A into T A plus B into T B, right? Now by definition, what is T of A? Here T is depending upon the matrix A. If T is depending upon A, then that will be equal to PAQ. Here T is depending upon this expression. So this will be equal to P multiplied with this expression, A into A plus B into B into Q. So this is A into P multiplied with this, P into A plus B into P into B and then Q. See, A and B are scalars, right? So this is A into this PA is now multiplied with this Q. PAQ plus B into PBQ. So which is further equal to A into what is PAQ? It is T of A by definition plus B into T of B by definition. By definition of T, which is given to us. So we have shown that T A into A plus B into B is equal to A into T A plus small b into TB. So hence we have shown that this is a linear transformation. So therefore T is a LT means linear transformation from V into V. And because this is a linear transformation from V into itself, so we write that T is a linear operator on V. LO means linear operator on V. Right? Okay. Let's discuss some important transformations. Number one is zero transformation. Let UF and VF be two vector spaces. The function T from U into V is defined by T of alpha is equal to 0. This 0 is a zero vector of V. Right? For all alpha belonging to U. So T defined by this is a linear transformation from U into V. So is a linear transformation from U into V. Now how to show that this will be a linear transformation? Just apply the definition. Let's take two elements from U and the scalars from F. Then A into alpha plus B into beta will belongs to U because U is a vector space, right? So by property, A alpha plus B beta belongs to U. Let's check what is T of, if I take this element from U. Now because T is a zero transformation, so T of this element will be equal to 0. Can I write this 0 as the scalar A into 0 plus the scalar B multiplied with 0? Can I write like this? Okay. So by definition, then this will be further equal to A into, can I write 0 to be as T of alpha by definition, because whatever element you take from U, when applying this T, we will get the answer to be 0. So whatever element I can take, that will be equal to 0. T of that element will be equal to 0. So we can write 0 to be as T alpha. We can also write 0 to be as T beta. So this holds for all the elements when belonging to U. So therefore we have written T alpha for this 0 plus B into, let me take this 0 to be T beta. So we have shown that this T of A alpha plus B beta is equal to this, which is the definition for the linear transformation. So we have shown that T is a linear transformation from U into V, and it is called the zero transformation and is denoted by, this zero transformation is denoted by the vector 0 or 0 cap, right? Next is identity operator. Let Vf be a vector space. The function I from V into V is defined by I of alpha equals to alpha, the identity operator, where this alpha is belonging to this V and we are also getting the same alpha belonging to this V. So this is for all alpha belonging to V. Yes, so this is a linear transformation from V into V, and the transformation I is called the identity operator. Because, why operator? Because the vector spaces are same. Whenever we have the same vector spaces, we use the word operator, and it is denoted by I. Here we have not written the zero operator. It is the zero transformation because the transformation is from two vector spaces U into V. Right, so we have written here zero transformation. But here we have the defined for the identity operator. That means the vector spaces should be same. The transformation is from V into itself. So please remember this. Third one is the negative of linear transformation. Let UF and VF be two vector spaces. Let T be a linear transformation from U into V. The corresponding, the sign for T is defined by minus T alpha. This is equal to minus of T alpha for all alpha belonging to U, right? So this is a linear transformation from U into V. Now since T alpha belongs to V, so this implies, because this T alpha belongs to V, then we can also write that minus T alpha also belongs to V. So therefore we can say that minus T is a function from U into V. Yes? Easy? Clear? Alright. So to show that this is also a transformation, let's take two elements from U and two scalars from the field F. Let me write minus T of A alpha plus B beta. I need to show that this to be equal to, what is that? A into minus T alpha plus B into minus T beta, right? Okay, by definition this will be equal to, because we know that when applying the minus T on alpha we will be getting minus of t alpha. That means minus of t, this expression, a alpha plus b beta. This is by definition. Now because this t is a linear transformation, please remember that we need to show that this minus t is a linear transformation. T is a linear transformation, I know that. So let's apply the definition for the linear transformation. This will be a into t alpha plus b into t of beta, right? Reason, t is a linear transformation because a and b are scalars. So I can write this as a into minus t of alpha plus b into minus t of beta. And by the definition of negative of linear transformation, this minus t alpha is minus t of alpha plus b into minus t of beta, right? So we have shown that minus t of a alpha plus b beta is equal to this right hand side. So therefore minus t is a linear transformation from u into v, right? And the linear transformation minus t is called negative of linear transformation t. Negative of linear transformation t, right? Okay, so here ends up the types of the linear transformation, and now we are going to read this very important remark. Let T be a linear transformation from vector space UF into vector space VF. Then, first remark, T of 0 is 0. Because the transformation T is from U into V. So this 0 on the left hand side belongs to U, and the 0 on the right hand side belongs to V, right? Please remember this. Second point, T of minus alpha is equal to minus of T alpha for all alpha belonging to U. Third, T of alpha minus beta is equal to T of alpha minus T of beta for all alpha beta belonging to U. These are all the results we have got from the linear transformations. And fourth point, T of A1 alpha 1 plus A2 alpha 2 up to so on An alpha n. So that will be equal to A1 T alpha 1 plus A2 T alpha 2 up to so on An T alpha n for all alpha 1, alpha 2, alpha 3 up to alpha n belonging to U, and A1, A2, A3 up to An, that belongs to the field F or the set of real numbers, right? So here ends up the first lesson. In the next content, we are going to discuss the range and null space of linear transformations, rank and nullity of the linear transformations, right? And also the rank nullity theorem. Okay, thank you. Stay blessed.